I was trying to explain the concept of modern data to a friend the other day, and I realized the old metaphors just don't work anymore. We used to say it was like drinking from a fire hose.
Which sounds painful, but, manageable if you have a strong jaw.
Exactly. But looking at the research for this deep dive, that's not it. It's more like standing under Niagara Falls with a thimble and trying to catch specific drops of water. Whether you're designing a VLSI chip with, 10 billion transistors or tracking ad clicks for half the planet, you are just drowning.
It's the sheer velocity of it. You're
Yeah.
talking about chips generating terabytes of switching traces in seconds, or marketing campaigns logging billions of events. We've hit what the industry calls the universal constraint.
I love that term, the universal constraint. It sounds
Well,
ominous.
it kind of is. It's the collision between data bloat, the fact that we literally cannot store every single cycle by cycle trace because hard drives aren't free,
Right.
and the need for absolute accuracy.
Right, because you can't just say, oh, we have too much data, let's just ignore half of it. If you miss that one critical voltage spike in a chip or that one massive trend in user behavior, the consequences are huge.
Exactly. For a long time, the engineering answer was just brute force, buy more storage, build bigger server farms. But we've hit a wall. Physics and economics have both said stop.
So the solution isn't more hardware.
It's smarter math.
And that is our mission for today. We're exploring the shift from exhaustive storage, keeping everything to streaming estimation. We're unpacking probabilistic data structures or sketches.
Specifically, we're looking at two absolute legends in this space: the count-min sketch, or CMS, and the hyperlog log, or HLL.
These sound like droids from Star Wars, but they
Yeah.
are actually incredibly elegant tools. We're going to see how they act as shortcuts to finding heavy hitters in chip power analysis and counting uniques in web traffic.
And the kicker:
The kicker is they do this with a memory footprint that is honestly shocking.
we are talking about replacing gigabytes of raw data with mere kilobytes of memory,
Kilobytes.
while maintaining about 99% accuracy.
Okay, let's unpack this. Let's start with the countmin sketch. The name implies it counts things and it minimizes something. But help us visualize it. If I could see a countmin sketch sitting on a desk, what am I looking at?
You're looking at a grid, a simple matrix, or a 2D array. I mean, just imagine a spreadsheet. It has a specific width, let's say a few thousand columns, and a specific depth.
Okay.
And the depth is usually just a handful of rows, maybe 5 or 6.
That's it, a small spreadsheet.
That's the whole structure. That is your entire memory allocation.
Okay, so I have this grid. Now let's apply this to the real world. The sources focus heavily on VLSI design chip making. Let's say I have a specific node on a chip, node A, and it just toggled on. It switched from 0 to 1. That's an event.
Right. And in a modern chip, you have millions of these nodes toggling billions of times. We need to track which ones are toggling the most, the heavy hitters.
So node A toggles. I don't just write node A in a list, do I?
No, that would take way too much space. Instead, we hash node A. We run its ID through a hash function. In fact, we run it through several different hash functions.
One for each row of the grid.
Exactly. If you have 5 rows, you have 5 hash functions. The first one takes node A and calculates a coordinate. Okay, you go to row 1, column 102. The second function uses different math and says you go to row 2, column 55, and so on.
And at those spots.
At each of those specific row call spots, we just increment a counter. We add 1.
Okay, I'm marking an X in 5 different spots on the grid. But here's the problem, and I know this is the core of the concept. If I have 10 million nodes and a grid that's only a few thousand columns wide,
Right.
aren't things going to crash into each other?
They absolutely will. That's a collision. Node A might hash to column 102, but node B might also hash to column 102.
Right.
So that counter at 102 is now counting toggles for both A and B. It's contaminated.
So if I want to know how many times node A toggled and I look at column 102, the number is going to be way too high. It's basically garbage.
It's too high, yes.
No.
But it's not garbage. This is the aha moment of the count-min sketch. Remember, we hash node A to 5 different locations.
Okay.
Because the hash functions are independent, it is statistically extremely unlikely that node A collides with other heavy hitters in all 5 of those rows.
I see where you're going.
Yeah.
So in row 1, it might share a cell with a really busy node. But in row 2, it might share a cell with a node that barely ever switches.
Precisely. So when you query the sketch to ask how frequently did node A toggle, you look at all 5 values in the grid that correspond to node A. Some will be huge because of collisions, but the smallest value, the minimum.
That one is the closest to the truth.
Exactly. Because collisions only ever add to the count, they never subtract. The error is always a positive bias. The minimum value acts as a tight upper bound. By taking the minimum, you strip away the noise from the other nodes.
That is surprisingly clever. You're using randomness to cancel out the noise.
Hmm.
And the memory savings mentioned in the notes are just wild.
They are. For a design with, say, 10 million nodes, storing the exact counters for every node would take over 4 gigabytes of RAM.
4 gigs.
A count-min sketch with 99% accuracy, about 54 kilobytes.
54 kilobytes, that fits in the L1 cache of a CPU. You've turned a storage problem into a math problem and solved it.
And that efficiency, it changes how engineers work.
Mm-hmm.
Let's look at the application in power analysis.
Right. The physics formula, P equals alpha times C times V squared times F.
You remember your physics.
I try. But the key variable here is alpha, right? The switching activity factor.
Yes. Alpha is a number between 0 and 1. It represents how often a node toggles. If a node is constantly switching, alpha is 1. If it's dead, alpha is 0. The problem is alpha isn't static. It changes based on what the chip is doing.
Are you playing a video game or just staring at a spreadsheet?
Exactly. And to find the peak power, the moment the chip gets hottest, you need to find the nodes with the highest alpha, the heavy hitters. Traditionally, you'd run a simulation and save a massive waveform file terabytes of data, then parse it to find the hot nodes. It's slow and storage heavy.
Well, but with CMS.
With CMS, you create a switching power sketch.
Yeah.
You stream the simulation data through it.
So the data just flows through the sketch, updates the counters, and then disappears. You don't store the trace.
You don't need to.
Huh.
The sketch retains the frequency data. At the end, you query the sketch. You ask, who are my heavy hitters? And it instantly identifies the nodes toggling the most. These are your potential thermal hotspots.
It's like panning for gold, but the river is moving at light speed. But the sources go deeper than just how often. They talk about spatial correlation.
This is where it gets really cool visually. Imagine breaking the chip layout into a physical grid squares of X and Y coordinates. You can assign a sketch to each region.
So instead of just knowing some nodes are hot, I can see this specific corner of the chip is on fire.
Essentially, it reveals thermal density. If physically proximate nodes are switching simultaneously, that's a heat problem. But we can also look at time. The notes mention a temporal switching analyzer using rotating sketches.
Rotating sketches, like one sketch for the first millisecond, another for the second.
Exactly. Buckets of time. This allows engineers to detect burstiness. A node might have a low average switching rate, but maybe for 10 cycles it just goes crazy.
Like a sprinter resting and then dashing.
Right. And that dash, that burst, creates a sudden demand for current. That causes a voltage droop, which can crash the chip. The sketch captures that variance.
The source material actually had a specific formula for this, the burstiness index. It was something like standard deviation minus mean over standard deviation plus mean. It's fascinating that you can derive that kind of statistical detail from these probabilistic counters.
It allows you to find the worst case workload automatically. You can compare a sketch from a gaming workload versus a video workload and instantly see which one is more bursty without rerunning massive regressions.
Now, speaking of voltage droop, let's pivot. This was one of the most clever twists in this entire deep dive, IR drop analysis.
Right, Ohm's law. V equals I times R. Voltage equals current times resistance.
Here's what confused me at first. A count-min sketch is for counting, counter plus 1. But for IR drop, we don't care how many times the voltage dropped. We care how deep the drop was, the magnitude.
You spotted the problem. If we just count drops, we miss the severity.
Yeah.
So they adapt the tool, they change the update logic.
How so?
Instead of counter plus 1, the logic becomes counter max, counter current drop.
Oh, I see. So the cell in the matrix acts like a peak-hold function on a stereo.
Precisely. It captures the maximum voltage drop seen so far for any node that's been hashed to that position.
But wait, go back to the collision logic. If my safe node A, collides with node B, which has a massive voltage drop,
then the counter will hold node B's massive drop value.
So when I query node A, the sketch tells me, hey, node A has a massive drop. It's lying to me.
It's giving you a pessimistic estimate. But remember the min rule. You check all 5 rows. Maybe 4 of them are contaminated by high drop neighbors. But if just 1 row is clean, you take that minimum.
And because the error is always a positive bias, it only ever overestimates the drop. If the sketch says the drop is safe, it is definitely safe.
Exactly. It provides a conservative upper bound. This enables what we call sketch-based sign-off. You use the sketch to filter out the 99% of nodes that are clearly safe.
And then
Then, you only run your expensive, detailed SPICE simulations on the top 1% of risk nodes that the sketch flagged.
You're using a blurry map to find the treasure and then pulling out the magnifying glass only when you're standing right over the X.
That is a perfect analogy. And you can do this from multiple corners simultaneously. High temp, low voltage, fast silicon, just by running parallel sketches. It's a multidimensional view of reliability that was previously impossible.
It really changes the game from store everything to estimate the important stuff. But let's shift gears. We've been talking about VLSI, power, and voltage. But the outline brings us to a completely different problem, the uniques challenge.
Yes. This is where we leave the count-min sketch and introduce its cousin, the hyperlog log, or HLL.
Which sounds like a very caffeinated log file.
It's a great name.
Yeah.
The problem here is different. In CMS, we care about frequency. In HLL, we care about cardinality.
Meaning, how many distinct items are in this set?
Right. Think about a marketing campaign. You don't care that the same user saw your ad 50 times. You want to know how many unique users saw the ad?
Or in a network, how many unique IP addresses hit the server?
Exactly. And counting uniques is surprisingly hard. If you want to be exact, you have to store every single user ID you've ever seen just to check if the next one is new.
And as your user base grows to billions, that database becomes massive and slow.
It's unworkable. So how does hyperlog solve this with, what was it, 1.5 kilobytes?
You know, it sounds impossible.
It uses a beautiful observation about randomness, the coin flip analogy.
Okay, walk me through the coin flip.
If I told you I flipped a coin and got heads, you wouldn't be impressed. It's a 50-50 chance.
Right.
But if I told you I flipped a coin and got 10 heads in a row.
I'd suspect you stood there flipping that coin for quite a while to get that sequence.
Exactly. The probability of a run of k heads is 1/2 to the k. It's rare. HLL applies this to data. It hashes your user ID into a binary string zeros and ones, and it looks for the longest run of leading zeros.
So if I see a hash that starts with like 5 zeros, 0, 0, 0 zeros.
That's somewhat rare. But if you see a hash with 20 leading zeros, statistically, you must have processed a massive number of unique items to stumble upon that outlier.
So the algorithm doesn't store the user IDs at all. It just remembers the longest run of zeros it has ever seen.
Simplified, yes. But to avoid getting lucky with one weird outlier, it splits the stream into hundreds of buckets or registers. It tracks the record in each and then averages them.
How does it average them?
Specifically, it uses the harmonic mean.
The harmonic mean, that's the math that smooths out the spikes.
Yes. And the result is that you can count billions of unique users with an error rate of about 2% using a fixed memory block that fits in your pocket.
That is just cool. But there is one more superpower that these structures share. The source material calls it lossless mergeability.
This is crucial for modern distributed computing. Imagine you have servers all over the world, New York, London, Tokyo. Each one has its own stream of data.
And I want the global total. How many unique users visited us worldwide?
If you were storing raw data, you'd have to ship terabytes of logs to a central server and deduplicate them. It's a nightmare.
But with sketches.
You just ship the sketches. You take the sketch from New York, the sketch from London, and the sketch from Tokyo. Since they are just small arrays of registers, you can merge them.
And for HLL, merging is just taking the max of the registers, right?
Exactly. And the resulting merge sketch is mathematically identical to if you had processed all the raw data in one place. It's a lossless merge of the estimators.
That allows for some powerful analytics, like the marketing funnel the sources described.
Right. Let's say you have an HLO display for people who saw the ad and an HLL website for people who visited. You can merge them to get the union, the total reach.
But what about the intersection, the people who saw the ad A and D visited?
HLL doesn't do intersection directly, but you can use the inclusion-exclusion principle.
Oh boy, set theory.
It's simple, promise. It's the size of set A plus the size of set B minus the size of their union.
And that gives you the intersection.
Simple arithmetic. You can calculate conversion rates or lost users, people who visited but didn't buy all without ever doing a database try.
And in the VLSI world, this applies to hierarchical rollup.
Yes, you can have sketches for individual standard cells, leaves of the design. You can mathematically aggregate them to estimate power for larger blocks, macros, and entire units without rerunning the simulation.
It's scalable from the transistor to the data center.
That is the key takeaway.
So let's wrap this up. We've looked at two sides of the coin. We have count-min sketch for finding heavy hitters, whether that's frequency of switching or magnitude of voltage drop. And we have hyperlog for finding cardinality unique counts.
And both represent a paradigm shift. We are moving from a world of exact, resource-heavy accounting to smarter approximation.
We are trading a tiny percentage of accuracy, a predictable, bounded error, for massive gains in speed, scale, and focus.
And focus is the important word. In a sea of noise, these tools help you find the signal. They tell you where to look.
I love the quote from the source material. In a world of infinite data, approximation is the ultimate optimization.
It really is. We're no longer limited by what we can store. We're only limited by how cleverly we can estimate.
So, for you listening, think about your own data haystacks. Whether you're debugging a chip that's overheating or trying to understand why users are dropping off your app, what are the needles you're trying to find? And do you really need to count every single strand of hay to find them?
Usually a sketch is all you need.
Thanks for diving deep with us. We'll see you on the next one.